Okay, YouTube, in this video we're going to consider what we call the trig form of a complex number. And up until this point, we've been considering complex numbers as these numbers we typically represent with the letter z. And we say that it is some real part plus some imaginary part. And having graphed a bunch of these in the complex coordinate plane, we see that really all it is that we're graphing the real part on the real number axis, what we formerly called the x-axis. And then we're graphing the imaginary part on the imaginary axis. We say the imaginary right here. But essentially you could see that this just forms a right triangle right here where we have some distance from this point back to the origin. That would be its absolute value of this complex number in standard form. We're calling this r in this case. And also this, we have some angle that would indicate the direction angle of this kind of, I guess you would call it hypotenuse of this triangle right here, this distance from the origin out to this number. So what we're going to do is we're going to rewrite this complex number in standard form, except for instead of writing a and b, which would tell us how many units right and up or maybe left and down or whatever, I want to rewrite these in terms of two things here, both the distance it is from the origin, or this distance r, and this angle theta that tells us kind of the direction that it's heading in. So to work with this, what we're going to say is, well, how could I, if I knew a and b, if I knew two parts of this triangle, how could I solve for a and b with respect to r and theta? And so I suppose we could say this. This is very true, actually. We say that if I were to relate this angle theta to a and b and r, then we could say that the cosine of our angle theta here would be equal to a over r. And so what we could do is we could say, well, solving for a here with respect to r and theta, we could say that a is equal to r cosine theta. R, which is that absolute value distance, times the cosine of just the direction it's heading in. So this is very fair to say. And likewise, it's fair to say that if we took the sine of this angle, we can see over here SOHCAHTOA-wise, we say sine is opposite over hypotenuse, then we would get b over r, where we could multiply both sides of this by r, and we're able to deduce essentially that b is equal to r times the sine of theta. So looking back up what we had up here, we could say that if a is equal to r times the cosine of this angle, and b is equal to r times the sine of this angle, then what we get is what we call the trig form of a number, of a complex number. And that would be rewritten thusly. I would say that a is equal to r cosine theta, this is our a here, plus b times I. This is our complex number where our b value here is equal to r sine of theta. So these two numbers really are the same things, except for in the first instance here, we say that this is a rectangular representation because it takes us left and right, up and down to get there. Whereas writing it thusly, we have r cosine theta plus r sine theta I. We have both the direction angle as well as the distance out from the origin going in that direction. So these are our conversions here. You'll notice that I wrote them on the left as well, but we say the conversions that are going to take our basically x and y components and rewrite them in terms of r and cosine, which are direction and magnitude to get out to there. So since we've made this substitution of r cosine theta and r sine theta in for a and b respectively, we get this trig form of a complex number. And so what this trig form is really good at doing is telling us, instead of how far left, right, up, and down to go, it's telling us how far to rotate and how far out to walk from there. So I do want to point this out. In this entire expression here, I have taken this I value and I've kind of displaced it to the front of the coefficient here, the coefficient being r sine theta. So we tend to write the I value in front of this just so that we don't think that that I is involved with the angle at all. And then also this, both of these terms have an R value in common. So it is entirely appropriate lots of times to write that R out front and then say cosine of our direction plus I times the sine of our direction here, where I is the imaginary unit, and we have now the length from the origin and the direction that we're heading in. So we have a length or R value, and then we have a direction. Okay, I'm going to clean this up even further now, and we are going to write this z value, since it is always r times cosine theta plus I sine theta. We get so used to this that we tend to write it as r times the CIS of theta. And when you see this right here, this is a really truncated way, or even r CIS theta. This is a very truncated or shortened way of writing r times cosine I sine, where we have our cosine I sine, and we're just implying that there is a plus sign in between the cosine and the I sine. So this RCIS theta, this is a wonderful thing because it means that if I were given a complex number in standard form, we could say 2 plus 5i. and I wanted to write this in trig form, then we could do this. We could figure out what direction it's heading in and how far it is from the origin. So let's go ahead and take this into consideration. We're 2 to the right, 1, 2, 3, 4, 5 up. So our complex number in standard form would be this number here. 2, 5 would be its components there. What I want to do is actually say, okay, well then what is this distance r here? And what are these components here? We would say that this would be our b, and this would be like our a. Okay, this is like our b and a. So if we're going to find this in trig form here, we're going to need to find two things about this. We're going to need to find this distance and this direction angle theta. So in terms of how could we find this angle theta in between here, we could just run a tangent relationship on this angle theta and work backwards with tangent inverse. So we could say that saying that the tangent of this angle theta here would be equal to 5 over 2, we would get theta, or at least the reference angle for this would be tan inverse of 5/2. And so we say 2.5, which is our 5/2 there. If we're going to do tan inverse of this, we get an angle of about 68.2 degrees. So about a 68.2 degree angle, okay? And we say, what is our r value here? We could just use Pythagoras to solve for r. So it's the square root of 5 squared plus 2 squared, which is the square root of 25 plus 4, so root 29. So if we want to write the trig form of this number, then we would say that it's equal to root 29 cosine of 68.2 degrees plus I times the root 29 sine of 68.2 degrees. And even simpler yet, we could take all of this here and boil it down to basically root 29 CIS 68.2 degrees. And all this is communicating is essentially that we are going this far, square root of 29 outward, in a 68.2 degree direction, which is this angle right here. But this is what we call the trig form of a complex number, and it's a great form because it just tells us what direction and how far to walk as opposed to left, right, up, and down to get to a number. Cheers.